and this is joint work with my advisor, Emery Berger. So before I dive into memory leaks on the web, I want to ask a philosophical question. What are memory leaks anyway? You might think that the answer is obvious, but it's actually surprisingly subtle. Let's consider manual memory management in a language like C or C++. When a developer needs some precious, valuable memory, they call malloc. And if the program no longer needs the memory, the developer needs to call free to let it go. Sometimes the program has memory that looks valuable and in use, but it's actually worthless, like an ineffective cache that it just doesn't need. And this can also be safely freed without impacting the program. It's up to the developer to determine when memory becomes garbage or worthless and to call free to release it. If the developer doesn't free some garbage or some worthless memory, it sticks around. And if this continues to happen, the program's heap becomes like an episode of Hoarders. In manual memory management land, failing to free garbage or worthless memory causes memory leaks. Automatic memory management ensures that certain kinds of leaks can't happen. Memory that is valuable to the program is reachable, and the garbage collector keeps reachable memory around. When the memory becomes unreachable and starts to pile up, the garbage collector automatically throws it all away, ensuring that garbage does not stick around. But what about worthless memory? If garbage is automatically collected, can a program have worthless memory? It turns out, yes, it can. Automatic memory management does not solve the problem of leaks caused by worthless memory. Just because memory is reachable does not mean that it is valuable. As a result, worthless memory can pile up in a garbage collected program with no problem. One approach for identifying worthless memory is staleness tracking. Objects become fresh when they are used, and eventually, they become stale if they have not been accessed recently. Stale objects are marked as potential memory leaks. Another approach to locate worthless memory is growth analysis. Growth analysis locates objects that grow in count or in size, assuming that continually growing things are unintentional and likely to be leaks. Neither of these approaches is a silver bullet for finding memory leaks in the presence of automatic memory management. Worthless memory can be reachable and accessed frequently by an application. A staleness-based approach will not find those leaking objects. Also, object growth does not always indicate a leak. Some growth is desirable, such as caches. Growth-based approaches may incorrectly mark those objects as leaks. What we really want is a semantics-based definition of a memory leak. An object source is leaking if deleting some of the objects does not impact the program's behavior, which indicates that the objects are in fact worthless, and if it retains an unbounded number of objects over time. However, there's a problem with this definition. How can we tell that the number of objects is actually unbounded and that they have no impact on the program's behavior? What we need is an oracle. This is the oracle at Delphi. An oracle promises to identify leak object sources and say, hey, what's with all this smoke? Get rid of it. It's not needed. It's worthless. In order to find this oracle at Delphi, we're going to need to travel to Delphi in Greece. The neighborhood's not quite what it used to be, but maybe we can find her. Maybe she's still around somewhere. And if we are to travel to Greece, we're going to need to find a place to stay. So I'll head to one of my favorite websites, Airbnb.com, and search for Delphi. After browsing for a while, though, I noticed something odd. The web page becomes slow and unresponsive, and it takes a long time to load pages. And eventually, the browser crashes because it's out of memory. Airbnb appears to have a memory leak, and this is a true story. This has actually happened to us, and we discovered it in the course of this work. And what we've also discovered firsthand in this work is that it's not just Airbnb that is suffering from memory leaks. Plenty of other websites and the libraries that they use suffer from memory leaks that degrade browser responsiveness over time. And in fact, over 99% of Google Chrome crashes on low-end Android smartphones are due to memory issues. These problems are not just a matter of speed. They can prevent visitors from spending time on a website. Today, the process of debugging these memory leaks is arduous. Developers typically examine and compare heap snapshots that display the live objects of the program. Here's a heap snapshot from Airbnb.com. Two of these object types are internal browser objects that website code does not directly manage, and they're unhelpful for a web developer. The other two contain every array in the program and every object of an unnamed type. And unnamed objects happen often as JavaScript is dynamically typed. And if I expand the view a bit, I'll find XN and other random names that mean very little to the developer, since the source code of the web page is minified and obfuscated to reduce the size of the JavaScript code. What is not evident in this view is where the worthless objects are and where the heap is growing, which heap items are unneeded and can be deleted. Identifying worthless, leaking objects is a huge challenge, even for seasoned developers. A Google developer closed a Google Maps memory leak issue in their bug tracker that over 100 developers voted on, and that's easily among one of the highest ranked bug reports. And they did that because it was infeasible to debug the leak. Things are looking quite bleak for debugging memory leaks in web applications. However, there is hope. Most modern single-page web applications, such as Airbnb, Gmail, weather.com, frequently return to the same visual state. And by visual state, I mean a literal view that the application presents to the user, typically corresponding to a specific screen. On Airbnb, I can click between the listing of homes for rent and a list of recommendations tailored specifically for me. And these screens are the core output of a web application. If the application's heap exhibits sustained growth after each visit to a specific screen, then the application likely has a memory leak. In other words, growth between visits to the same screen is a strong indicator of a leak. And this growth can be used as an oracle to identify worthless memory. This insight is central to BLeak, an automatic memory leak debugger for web applications. BLeak uses growth between round trips to the same visual state as an oracle to identify leaking objects. Because we have this oracle, BLeak exhibits high precision. On a corpus of real production web applications, over 90% of the leaks reported are true leaks. The leaks that BLeak finds also have high impact. We've found large leaks in production web applications. BLeak also identifies the source code that is directly responsible for causing each leak, which dramatically simplifies the process of fixing them. To use BLeak, a developer must write a short input script of about 40 lines of code, which I will describe momentarily. And this script drives the application in a loop through distinct visual states. This is the sole input to BLeak. The rest of the process is completely automatic. This is the input script that I wrote to run BLeak on Airbnb. I don't expect any of you to read this, but I want to note that it's only 17 lines of code. And this script forms a simple visual state machine, where each visual state has a check and a next function. Let's briefly look at one of these states. This is the visual state corresponding to the Airbnb page with recommendations for me. The check function returns true when the application has finished drawing the visual state. In this case, it's quite simple. It verifies that the For You link at the top of the web page is selected. The next function transitions the application into the next visual state. So for Airbnb, it clicks on the Homes link in the top navigation, and that's it. Zooming back out, BLeak executes the input script in the following manner. BLeak first waits for the application to load and display the For You screen. Then it transitions to the home screen. BLeak waits for the application to finish displaying the home screen before transitioning to the For You screen. And then with this, the loop is closed, and now we have a way to run the application in a loop. And as mentioned before, the developer only needs to provide that input script to BLeak, and the rest of the process is completely automatic. BLeak loads the application in Chrome and commands the browser via the remote debugging protocol. Chrome is configured to talk to a BLeak-controlled proxy, which performs JavaScript rewriting needed for memory leak debugging. And with this architecture, BLeak can diagnose memory leaks in unmodified web applications in production that we don't control, just like Airbnb. Using BLeak, I have found, reported, and fixed over 50 memory leaks in a wide variety of popular web applications and libraries, including Airbnb, jQuery, and AngularJS. All of these leaks were completely unknown to us and to application developers. BLeak identifies memory leaks by looking for growing objects in the heap between round trips to a visual state. I want to stress that a heap graph alone does not make memory leaks obvious. Here's the heap graph for about blank, which is a blank web page. It has tens of thousands of nodes and edges, and these all correspond to internal browser objects. You may be wondering what the heap graph for Airbnb looks like. It looks like this. So this is the actual screenshot of the graphing program, Gephi, struggling to display the heap graph. There are over 800,000 nodes and 4 million edges in the heap graph, and we have no idea which are responsible for leaks. So, for the purpose of this presentation, I'm going to dramatically simplify the graph, which will give away a major leak that we found. And while I do that, keep this image in mind, because leaking objects are far from obvious. So, the first visit to Airbnb's home screen yields a heap graph like the following. Using the developer-provided input script, BLeak runs the application in a loop back to the home screen and takes another heap snapshot. Now, 3 objects have grown since the last visit. BLeak marks these as potential memory leak routes. BLeak repeats this process multiple times, typically for a total of 8 round trips, to filter out objects that grow to a fixed size. At the end of this process, BLeak identifies a set of leak routes which are responsible for leaking memory, including these 3 large map objects, which we had no idea were leaking going into this. Also, in that non-simplified heap graph, each of these maps is actually a very large subgraph of many small objects. So this leak, again, is very far from obvious in a heap graph. So now that BLeak has identified growing objects, these leak routes, it needs to rank them by importance so developers can spend their time fixing memory leaks that actually matter. And while I am only showing 3 leak routes on this slide, there may be many more for the developer to prioritize. And in fact, we found 32 distinct leak routes on Airbnb.com. One possible ranking metric is retained size, which is the quantity of memory that would be collected if a leak route were garbage collected. This is a standard metric that many tools use. The global variables window and document are not garbage collectible, so they're not relevant to the metric. The problem with this metric is that objects shared between leak routes, like these very large map objects, are not captured by this metric. Fixing a single leak route will not garbage collect them, and so no leak route gets the credit for them. As a result, retained size, in this case, actually ranks the history leak route, which is an array of strings, above the event listener leaks, which collectively retain multiple megabytes of map memory. Essentially, retained size misrepresents the impact of memory leaks. BLeak uses a new metric that we call leak share to measure the impact of memory leaks. Leak share splits the credit for objects shared between leak routes, and the algorithm is conceptually simple. First, leak share ignores objects that are reachable from non-leak routes, because these are not leaked objects. Second, for each remaining object, leak share counts the number of leak routes that retain it. In this example, each map is retained by 2 leak routes, while everything else is only retained by 1. Third, leak share splits the credit for each object evenly between the leak routes that retain it. The end result is that the event listener lists, which leak large map objects, are correctly ranked above the history array. Leak share focuses developer effort on memory leaks that provide the biggest return on investment, meaning the developer spends less time developing fewer fixes that free more memory. To diagnose the memory leaks, BLeak reruns the application in a loop and collects stack traces when the leak routes grow. BLeak collects a stack trace when the application adds an item to a leak route, causing it to grow. And if that item is later removed, BLeak removes the stack trace as well because the application has responsively managed its memory. And to collect these stack traces, BLeak uses JavaScript reflection and program transformations. And these stack traces point directly to the code responsible for each memory leak. At the end of a BLeak run, BLeak produces an interactive report that describes its findings. On the slide is the report that BLeak produced for Airbnb.com, the production website, during our evaluation. Let's take a closer look. At the top of the report, BLeak quantifies the amount of live heap growth that it observed in Airbnb.com. It appears that Airbnb's live heap size increases by a whole megabyte every time we return to the home screen. True story. Below the heap size graph, BLeak lists the leak routes found, ranked by leak share. Fixing the topmost leaks should provide the greatest return on investment. And if we click on one of these leak routes, the panel expands to reveal a list of stack traces that were recorded when the leak route grew. These stack traces directly identify the code responsible for growing that leak route and thus for the memory leak. Next to the leak route listing is the complete JavaScript source code of the web application collected during BLeak's run. The source code viewer comes complete with a pretty print function, which makes minified JavaScript somewhat readable. Just to give you an idea of the complexity of modern web apps, Airbnb ships with over 3 megabytes of minified and obfuscated JavaScript. And if you pretty print it, it comes out to about 175,000 lines of code. So finding memory leaks in this code base is like finding a needle in a haystack. Clicking on one of these stack frames in one of the stack traces, like so, causes the source viewer to jump to the line of code that the stack trace represents. This is pretty small, so let's zoom in a little bit. This JavaScript statement, highlighted in yellow, inserts a new global resize event listener every time we revisit Airbnb's home screen. Each of these event listeners retains a large map. This leak can be fixed by adding an explicit cleanup handler to the Google Maps library that removes the resize event listener prior to navigating to a new screen. Overall, BLeak reported 32 leak routes for Airbnb.com, and of these, only 2 were false positives, corresponding to objects that grow to a fixed size, but we didn't observe it stopping the growth during 8 runs. Using BLeak's output, I was able to implement fixes for each of these leaks and test them locally by injecting them into the web page using BLeak's proxy. Each of these fixes took about 10 minutes to develop since BLeak pointed directly to the code that was responsible. And fixing all of these leaks eliminated over a megabyte of heap growth per round trip, which reduced heap growth by 80% for this particular application. Guided by BLeak, I was able to develop a fix for the Google Maps memory leak, and I provided the developers with all the information required to fix the bug, and also happily provided many developers with workarounds for the bug, and they're very happy with that. We also ran BLeak on a variety of other production web applications. This line represents live heap size over round trips through a specific visual state with no leak fixes in place for each of these evaluation applications. You can clearly see that all of these applications have memory leaks. This dotted green line is the live heap size after fixing all of the leaks that BLeak reported. We don't know how many leaks there are that BLeak did not find, but it's clear that fixing the leaks significantly decreased heap growth. And in fact, fixing BLeak reported leaks reduced heap growth by an average of 94%. We believe that the core ideas in this work are useful beyond web applications and can be used to find memory leaks in other types of GUI applications, such as mobile applications and native GUI applications. We plan to explore this area in future work. So I just told you about BLeak, an automatic memory leak debugger for web applications. BLeak is open source and can be found at bleak-detector.org. Thank you all for your attention.
I'm Hannes, working on V8 and Chrome. The web is indeed leaking, so this work is really impactful, really cool.
Thank you.
To see that talk. Have you thought about automating the input script? Because, like, you know, many web pages have infinite scrolling. If you tend to scroll down for a while and go back up, they build up a huge DOM tree. Or you could find like links and just walk through them and then use the back button to go back. Have you thought about automating that step completely?
Yes, I actually have. There's been some great work in the PL community on synthesizing scripts for like web scraping, for example, which deal with a lot of the issues required to produce these input scripts. So I think that that work is very harmonious with this work, and that it might actually be feasible to automate creating them.
Yeah, I think that would be super useful for many developers who have no idea what a memory leak is.
Completely agree. Thanks for the question.
Yeah, very cool work. I have a very specific question, and if you say, look at the paper, I'm happy with that too.
Sure.
How do you efficiently compute the leak share metric? If you have a very large graph, it seems like that could be very expensive to compute.
It's only very expensive, so it's basically order n, as long as there's not significant overlap between all of the leak routes. So if, in like the worst case, if all of the leak routes leak the entire heap, it might be pretty expensive in the worst case, but that doesn't typically happen in practice. So I haven't had an issue with it scaling.
Thanks for the excellent talk and really interesting work. I was wondering, having looked at loads of these leaks, are they idiomatic, and would there be any possibility for better design patterns or programming language features that could help avoid them in the first place?
Yeah, so I think it has to do with how these applications are constructed in the first place. Because it's garbage collected, people don't realize that in some cases you have to actually explicitly remove items after you insert them when you're transitioning to new web pages. And while modern GUI frameworks like Angular and React, they have a notion of cleanup handlers, developers aren't conditioned to actually create them. So I don't really have an answer for how we could solve this from the programming languages standpoint. But it is idiomatic, and I think that's why we find why it's so prevalent in the wild right now.
Hi. Instead of sharing credit for leaks, did you consider providing a relation so that you could say you have to fix both of these? You have to fix the leaks associated with both of these routes in order to recover this shared object.
I don't know how I would compute that efficiently, because while most of the subgraph is shared, there's always a few objects that are only owned by a particular leak route, like the particular functions that are leaking the maps in a closure. So I don't know how you would efficiently compute those and present that in a meaningful manner to the developer. I feel like more information would just be more confusing in that case.
But when you worked through your 32 leaks, presumably you didn't garner the benefit from your effort until after you got, say, the second or third one, when there was a shared object involved. Is that right?
Yes, yeah, those maps would not be freed until you fixed all the leaks that leak them. But programmatically, looking at the heap, I think it would be difficult to present that information to the user in an intuitive fashion, that you have to fix these 3 leaks to free this much memory. Perhaps there is a way, but I don't see it immediately. I don't think it's immediately obvious to me. But happy to chat further.
John again.
Thank you.